The final presentation, set of presentations today will be a panel discussion by the Notre Dame faculty on how they are transforming waste to meet our energy needs. Today's session will be moderated by Professor Jennifer Schaefer. She's a professor in the Department of Chemical and Biomolecular Engineering. And I'll now hand it over to Professor Schaefer, and I'll come back at the end. So Professor Schaefer.
Thanks, Subhash, and welcome again, everyone, and good evening. I'm glad you could join us tonight for our panel discussion. Again, the topic is transforming waste to meet our energy needs. Our first speaker this evening is Professor Brenner, the Senior Associate Director for the Center of Research Computing, and he's going to be telling us about cyber infrastructure, energy consumption, conservation, and reuse. Paul?
All right, I will take it from there. Thanks, Jen. So my world as a computational scientist lives to the left and the right of me. So these are actual photos from the Notre Dame data center down at Union Station, where you can see roughly 5 or 6 racks. There's currently about 73 racks of compute infrastructure at the university. And what we found was we wanted to figure out ways in the past decade or so that we could figure out how to not only reduce the energy consumption, but are there ways we can reuse or to be better stewards of that, so the environmental, the impact. And give you a global scale, 2018 data center power consumption was about, depending upon which report, anywhere from 1 to 2% of the total global electrical consumption. And so once you get into a couple percent of the total planet's electrical consumption, it gets to be pretty significant. To convert that, that's 205 terawatt hours, right? So not kilowatts like you pay on your home, or megawatts that we think about in an individual data center, and that's not gigawatts, that's terawatts, right? So when you move 9 zeros from what you're used to on your household kilowatt hour bill, it is a significant number. Using US conversion rate at about 13 cents a kilowatt hour, it's about a 27 billion a year burn just on, and it's just the utilities, right? That's not any of the computer costs themselves. That is the power in and the cooling bill to keep those from overheating. So what can we do to do that particular effect? And this is primarily in the data centers. A lot of us are familiar with, right, as our lives become digital, we've obviously got the power consumption of our phone. We've got these Internet of Things, the power consumption of our Fitbits, right? I haven't worn this in years, so that's probably bad in Fitbit style, but I did find it so that I could pull it up here for this talk. But we've got this Internet of Things. Now, interestingly enough, those are very, very low power. So I'm going to be primarily talking about what's going on in the data center, because a lot of our phones, a lot of our laptops now actually offload that back to the data center. Our home security devices are talking and taking pictures and pushing it back out to the data center. So the data center is really the hungry beast globally as our world becomes sort of more data rich, more Internet of Things. And so the good and the bad news of that, over the past 10 years, the numbers show from 2010, 2020, that's only grown in terms of power consumption, only about 6%. And so it's not out of control. We've been able to kind of keep it, but there was a hope in 2010, if you had talked with folks that were assuming it would go down, right? And it didn't go down. In fact, the total number of compute instances, depending upon how you measure a compute unit, went up about 500%, right? So not 50, 500. So it's 5 times more. Now, a lot of that is great, advanced in computer architecture, right? So we're, 5 times, 500% faster, more compute capability. And we only went up 6% in power consumption. So there's a lot of benefit there as a computational scientist about better architecture that can do some of these computations as we come this machine learning, this data rich sort of environment, but it's still growing, right? And we're at 1 or 2% and we're growing, on a given year. So what are we going to do, in this environment? Some say do nothing. Some say, yeah, we'll eventually, we'll get this down. No one will need more compute power. We've gone 500% in the past 10 years. We're good. I'm looking around at some of the faces, and if I had to tell Bill, there's no more compute power, we're good. There are certain faculty on campus that would be very disappointed in the Center for Research Computing and Research, computational research as it goes, and we say, this is it, we will never provide you any more compute power, right? And so as researchers, we see that in terms of, we want greater complexity and richness of our models, or we want to go to you know, a larger scale that we've never done before. There are all these sort of grand challenges in modeling and data science. So we need actually this infinite amount until we've solved all of these other challenges out there. So we see no reduction in the hunger for compute power, despite some saying, look, we've got all we need, right? Some people thought you never need more than 512 megabytes of RAM, right? I'm aging myself, but right, that's all you would ever need. Your whole life would be sufficient there. So we see this continuous demand. So for those who say, look, it's not going to grow, there's no growth in demand, so from here on out, we'll have better architecture and we'll drop power. We don't see that. We haven't seen it over the past 10, 20, 30 years. We see an increase in demand, and we see trying to get more efficient. So what do we do if we're going to be another decade at this, you know, 200 terawatts? What can we do with that? So most know that the majority of power that's coming into IT equipment comes in as electrical energy, and it comes off as thermal heat. And so we spent some time over the past decade looking at options and how we can, you know, reuse or utilize or more effectively in any way leverage all of this excess heat, because not only are you paying the power bill in, but we're paying for all this air conditioning, et cetera, to get rid of it. So a couple things that the industry has been doing, and we've fortunate through a couple of, you know, collaborations, and I don't see, he's not on here tonight, but also with David Go, we've had some publications in this from both computational and from a thermomechanical, and Amy Bucelato in architecture over the past decade, looking at how we would reuse this in data center and buildings where we could do. Some of you have been at the university long enough to know at one point we were moving equipment, helping out, say, like a local greenhouse and various applications there. The challenge for doing this is, one, it's low-grade heat. For anyone who's worked in writing heat and energy reclamation, low-grade is hard, right? So if I'm going to cool the server and like to run around 60 and I'm only going to bop up the temperature to 90 F, if we could do a whole lot of great stuff at 90 F, we would just sit around in Texas and convert, you know, 90-degree, you know, air into electricity, and we'd all have this problem solved. But the low-grade heat is hard to use. So one of the things, you know, we've looked at initially was how we could get this up to higher, you know, output temperatures. And we were fairly successful, and the industry kind of followed along. We helped do some work with Dell and some other major companies. We said, look, can we run, we don't need to run data centers at 55, 65 degrees anymore. Can we run our data centers at 70 or 80 or something along those lines? And so that's pushed it up, you know, so picking up just 10, 20, 30 Fahrenheit coming off those servers has been helpful. Also, people have been doing it. I don't have time in this in my little 10-minute spiel. There's been talks of, you know, liquid, and there's, you know, various mineral oils, that sort of thing that can do the thermal conductivity at higher rates. But primarily we've been focused on air cool and what we can do with that, and helping redesign where that, you know, is most effective. The other problem is temporal. Up here in the north, we have a better opportunity that we at least don't have to put the big power bill into the cooling side of things, so that we can, you know, use fresh air. There's lots of different ways that we can do, you know, mechanically or electromechanically do the cooling more effectively. You know, and then repiping this into buildings. Like I said, the biggest is, where do we reuse this? Can we, you know, pipe it to a greenhouse in the north that needs it year round? Can we provide it to larger buildings, larger facilities? And we do a lot of that now today. Kind of our steady state is at Union Station. Quite a bit of that, you know, heats the full facility throughout the colder months. Still during the summer, we have a certain amount of cooling that has to happen. We're not 100% fresh air, but we've definitely mediated some of that over the time. And so, you know, as I kind of do a quick summary, and we can come back certainly during the panel discussion for those who would like to talk about this deeper, but, you know, we look at kind of like what we teach our kindergartners in the enterprise IT world and at the university, right, is, and it comes true, it's reduce, reuse, recycle, right? So if we can get better architectures, right, if we can continue to refine the chipsets, the algorithms, the memory pipeline, et cetera, within the computer itself, and reduce, to do X computation, reduce the amount of energy that takes, you know, that's game number one, reduce the amount. I'm not going to say, if you're waiting for me to say reduce the computation, that is my lifeblood. I am never reducing the computation if at all possible, but if we can do it at lower energy, absolutely. So reduce the consumption, you know, reuse it. So it's low grade heat, but just pipe it right back into, find out ways to locate your data centers with particular facilities that would need that low grade heat. And then, you know, order of magnitude, one more down the step is to recycle. We all know recycling's hard, right? There's a cost to doing recycling if we can't, you know, directly reuse it. And the low grade is going to be really expensive. We looked at ways that maybe, you know, heating water, getting the water to do, you know, back end, that's a longer grade storage of the energy. But those, at least as an industry standard, still aren't there. So the industry right now is still in the reduce and in somewhat in the reuse. We're not quite to the recycle just because we haven't found a good way because it's low grade. But that's the current sort of, you know, what's going on in trying to knock down that 27 billion a year power bill and where we can reduce, reuse, and recycle it. And I will stop there. And then later on when we get back to the panel, happy to answer any questions.
Thank you. We do have a moment now for a question. If anyone has one, please feel free to unmute yourselves. I'll pause for just a second. No questions. Professor Brenner, maybe you said previously and I missed it. Do you know on the Notre Dame campus, what percentage of our power is used for computing? Do you have any idea?
Sure. So, well, I can, instead of percentage, I can tell you it's a, we don't post it publicly, but for this audience, our power bill is roughly $750,000 a year just for the utilities on the core data center infrastructure. So we've been doing a lot to try and use better architectures, better systems, et cetera. And we've been flirting with that 750. We're trying to stay under it, but over the past 10 years, and with an increase in capacity too, we've gone from about $500,000 a year in power and utilities to about $750,000. So it has been, we've been growing more than the 6%, but in fairness, we've also been growing quite a bit in the computational capacity beyond what I already mentioned in terms of the linearity previously. So about $750,000 in utilities power bill.
Thank you. All right, so our next speaker this evening is Professor Nerenberg from the Department of Civil and Environmental Engineering and Earth Sciences. And tonight he's going to tell us just a bit about membrane-biofilm photobioreactors for biofuel production from waste CO2. And so I'm going to go ahead and share the slides. All right, Professor Nerenberg.
All right, Jen, thank you. So thanks for having me as a panel speaker tonight. I'd like to say a few things about a topic that we're working on in our lab. And it's addressing a new way to try and take advantage of waste CO2 and put it to use for something actually that can create energy. So just a quick review. As you probably know, algae are present in the environment and they are able to capture the energy from the sun. They fix carbon dioxide that's present in the air and they produce organic matter and oxygen. And that organic matter can settle to the bottom of a lake and eventually decompose and form gas or crude oil, which is a form of energy. So in essence, these algae are capturing the sun's energy and transforming it into another source of energy. There's a few transitions there, Jen, but I think maybe just go to the next slide. So there are a number of ways that people can use algae. They can use it for carbon sequestration, wastewater treatment, biofuel production, and even producing chemicals of value, pharmaceuticals, pigments, and so on. But I guess if you hit the next button, I'm going to focus here on the idea of using them for biofuels. So next, please. There are two kinds of ways that algae are cultured. There are suspended growth reactors and biofilm reactors. And I guess the most common type are these suspended growth reactors, as you can see in the picture on the right. And in those situations, the algae are grown suspended in the water. at relatively low densities. So they naturally form at a density of about 0.5 grams per liter. So when we want to harvest those and use them beneficially, we need to concentrate them first. And that often involves some kind of a coagulation, flocculation, and centrifugation, which actually requires more energy. So an advantage of the biofilms is that they form these dense aggregates of algae that are already at a high density, similar to the density that you'd get after the concentration of the suspended algae. So it can save a lot of energy from that respect. It also is more compact, has a smaller footprint and lower volume. So there are several advantages to using the biofilm reactors. Next, please. As just an example of one, it's just a big rotating drum with, in this case, cords on it, and the algae grow on the cords. And they can be harvested just by scraping it off. Next, please. Now, a couple of problems with these biofilms is that they need to sequester CO2 from the atmosphere. And the atmosphere doesn't have that much CO2 in it. Also, you can see from the plot on the right that CO2, when it's in water, changes its species from CO2 to bicarbonate to carbonate. And the algae only use the form of CO2. If you click next gen, there'll be a little arrow that shows up. At pH of 8, there's not that much in the form of CO2. Also, the algae tend to increase the pH as they metabolize sunlight. So one concern is this CO2 limitation and pH shift. Another issue is the oxygen inhibition. So as you saw previously, next, the algae produce oxygen as a byproduct, and it can inhibit the CO2 sequestration because it competes with the same enzyme. So I get a next for another transition there. Competes with the Rubisco enzyme. Next again. And again, you can see that they form oxygen as they metabolize. If we have a biofilm and have all these algae next to each other, it's like having a data center with all the processors stuck next to each other producing a lot of heat. That heat accumulates and doesn't dissipate. The oxygen accumulates in the biofilm, doesn't dissipate, and can cause inhibition. Next, please. What we propose doing is using a new support for growing algae, and we call this a membrane-biofilm photobioreactor. In this case, instead of relying on CO2 diffusing from the liquid into the biofilm, we supply it through a hollow fiber membrane that we pressurize with CO2. Now, this CO2 can be taken from a stack or from a treatment plant from some waste source and be delivered directly into the algal biofilm. I think if you hit next, there'll be a, yeah, so there's our CO2. And the advantage is we have much higher CO2 concentrations, allowing the algae to grow more quickly. The CO2 buffers and actually drops the pH within the biofilm, preventing this shift to higher pHs, which limits their activity. And also, in the same way that CO2 diffuses from the membrane into the biofilm, oxygen can be stripped out of the biofilm back into the membrane. So we can avoid this oxygen inhibition. Next, please. Here's a picture of this membrane biofilm photobioreactor in the lab. It's pretty small. It's probably like, this one's like 3 or 4 inches long. If you click again, Jen, you'll see another view of it. And you can actually see the hollow fiber membranes covered with green algae in the interior, kind of going left to right inside that flow cell. And yeah, next again, please. So we've done some experiments and done some modeling, and our modeling shows that, in fact, we get a significant increase in the growth rates of these algal biofilms when we supply the CO2 from this membrane. So the plot on the right, and I think if you click next, there'll be an arrow that shows up there. That's what we get as in the algal biofilm thickness over time when we supply the CO2, as opposed to that blue line on the bottom when we don't supply the CO2 from the membrane. Next. And we also did experiments. Here's a picture of the reactor on the light. We have a light source on the top. We have a flow cell with the membranes, and the algae grow in this flow cell. Next, please. And again, here's some pictures. We have the algal biofilm growing on the membranes on the left, and on the right we have a optical coherence tomography image where we can kind of get a CAT scan. We can see the membranes on the bottom and the algal biofilm growing on the top. Next, please. So, in conclusion, we think that this membrane photobioreactor can enhance the rate of algal biomass production. And the advantages is it avoids CO2 limitation and minimizes oxygen limitation, leading to higher growth rates. And because it supplies CO2 directly to the biofilm, as opposed to trying to bubble and transfer it into the bulk liquid, which would be very inefficient and also lead to loss of CO2, this utilizes it extremely efficiently. It's going exactly where it's needed and it's consumed in the biofilm. One more transition. What we'd like to do next is take the next step and see, now that we have the reactor and shown that it grows more quickly, how can we use this for actually looking at biofuel production, for example, producing lipids that then can be extracted and converted into biofuels. So that's kind of the next step that's waiting to happen. So I guess with that, I am done and happy to take any questions.
Fantastic. Do we have any questions right on hand right now?
Can I ask one?
Absolutely.
Wondered, do you know anything about the photo efficiency, Rob? You know, what fraction of photons that coming in actually getting used? So,
That's a good question. No, we haven't evaluated that. I'm trying to think if it would be different from a regular algal process. I suppose it depends a little bit on how it's operated, but I think, you know, I don't see why it would be different from any other algal process from that respect. So how much of the photons from the light are actually harnessed and converted into algal biomass? I don't have an answer to that question, but I don't see why it would be nor better nor worse than a conventional process.
do you have a sense in a conventional process?
No,
Yeah.
but I'll look it up and let you know.
Right, fair enough.
We're more biofilm people, so this photo reactor is a little bit new for us, but we find it really and promising.
Thank you. I think photosynthesis is actually a low efficiency process, if I remember correctly.
Yeah, I'm not sure how it compared to a solar panel, for example. You know?
I have a quick
I believe
question.
it's less.
Oh,
So-
yeah, it's less, yeah.
Yeah, this is,
Solar,
Which is,
go ahead.
oh, sorry, this is Ian Lightcap. Just wondering about if on these, or thought about running them vertically and just once the biomass builds up, just letting gravity, you know, peel them off so you have a passive process for collecting.
yeah, I mean, that's a really interesting question. So I think that leads to an important question, which is how do you harvest the biofilm when it's ready? And, you know, the answer is, I guess we don't know exactly. One thing that I've seen done in conventional biofilm processes that are grown in tubes, tubular photoreactors, is they pass, I think they call it a pig, like a block through it, and that scrapes the biomass off the walls. I don't know if you were to grow it vertically, if the weight of the biofilm and the strength of the biofilm would be such to really fall off when it reached the right thickness. Actually, with our modeling, we've been trying to estimate what is the optimal thickness at which we'd like to harvest it. Because if you harvest it when it's very thin, then you're harvesting frequently. If you wait till it's too thick, then the interior portion probably isn't active because the light doesn't penetrate far enough. So there's some kind of optimal thickness where you'd like to harvest. There's also probably a residual thickness that you'd like to leave because you need algal biofilm to produce more algal biofilm. So these are all good questions, and I don't have a good answer, but I think they're very interesting questions and important ones that we'll need to look into eventually.
I had a question.
Sure.
Have you looked at how, you mentioned that you were looking down the road at using these maybe as an effluent from traditional combustion, right, or CO2. How robust are the membranes in the algae to the other byproducts that you would get off of that combustion, like carbon monoxide, NOx, SOx, those types of things?
Those are all good questions. So yes, I don't know for sure that we could use the combustion right off of the stack without any prior treatment. You know, there's also biogases produced at anaerobic digesters and wastewater treatment plants that also, you know, have, you know, sulfide or you know, siloxanes or other things that could be detrimental. We haven't gotten that far yet, but I think kind of pretreatment would be needed, but we don't know for sure at this point.
Thank you.
That sounds great. I mean, hurry up and wait until so we're good.
Thank you. All right, so in the interest of time, we'll move on to the next presentation, which is from Professor Schneider, Chair of the Department of Chemical and Biomolecular Engineering, who will be telling us about the CISTAR Center.
All right, thank you, Jen. Thanks for the invitation to tell you a little bit about CISTAR. So I'm going to kind of approach things from a little bit more macro perspective than the previous two talks that motivate what we're doing in CISTAR. So, you know, at a high level, the types of problems that we're trying to deal with as a society is to get from what you see on the left, our sources of energy over the last century or so, which are largely fossil fuel based, very carbon rich. Oh, you're zipping too quick for me, but that's okay. And to move to a regime in which our energy comes from renewable, low or no carbon footprint sources, like solar cells or wind. Now, you know, it might be nice to say, well, we'll just stop doing the things on the left and start doing the things on the right. But when you look at the scale of energy usage, you realize that it's just not plausible, that we need a bridge to get from the left to the right. Now you can click to the next. So that's really the question, is how do we manage transition? If we're all the way to the right in 100 years or 80 years, whatever it's going to be, how do we manage that? And so that's part of the point of CISTAR. And I would argue, and I think that the evidence is very strong, that we're not going to stop using hydrocarbon fuels anytime soon. And if you look at things like the graph on the right here from the Energy Information Administration, which makes projections about energy use, you see projections are that we'll continue to use natural gas, liquids, even oils and such, well into the future. Things like hydro and nuclear and others are important, but the energy need is so great that we're not going to satisfy it all immediately. And again, then the challenge is, well, how then to continue to provide ourselves power, but do it in a more environmentally friendly and sustainable way. So over the last 15 years or so, the United States has been presented with a new opportunity. There's been the realization, not really the realization, but the technologies that have allowed us to access hydrocarbons that aren't available in other parts of the world, but are available right here in the United States in the form of shale gas. And I know you've maybe heard a lot about fracking and shale and so forth, and certainly extracting energy from the earth always have to be done in an environmentally responsible way. But I think, again, it's safe to say that we're not going to stop doing that altogether anytime immediately. So the point of CISTAR is to take advantage of these newly found shale resources and use them in a way that helps us manage this transition to the new energy future. So you could go to the next one, Jen. So what is the challenge with shale gas, short of getting the gas out of the ground? Well, the real scientific challenge, and the one we're trying to address, is that the types of feedstocks that you get out of shale are very different from the types of feedstocks than say coal or petroleum or what have you. Shale gas contains a lot of small molecules. People remember from their organic chemistry from long ago, there's a picture of a methane molecule, an ethane molecule, a propane molecule. These are small, they're gaseous, at ambient conditions. They're not a solid like coal or a liquid like petroleum. Unlike oil fields, which might be in one location and drawn on for a long period of time, the sources of shale gas are remote, as I just showed you. They're scattered all over the United States, even here even in Indiana, and so that raises a challenge in how to take advantage of something that's distributed so far and wide. That's in large part why you'll see things like flaring happening, which is a real waste of energy that in some of these places where hydrocarbons are being taken out of the ground, some of these small molecules are being released, and there's nothing to do with them other than to set them on fire. And so that's a serious waste. And why is that so? It's because these are intrinsically unreactive. So they're gaseous, they're hard to move anywhere, and they're unreactive, so they're hard to do anything with. Could you click to the next slide? What you would really like is not those small gaseous molecules. What you would like are things that we could use productively. Maybe as a fuel that's coming from a cleaner resource, maybe as monomers that can be used in making a plastic or something like that, maybe a chemical feedstock, like even the hydrogen that I'm showing you here, or other things that might be produced. And the advantages of those things on the right is those are condensable materials. That means they're easily transportable. They're much more versatile from a chemical perspective than the things on the left. And if we manage this process in the right way, we get to those useful endpoints in a more sustainable, lower carbon footprint way than we do, say, with getting petroleum from the Middle East. Could you click next? So CISTAR, the vision of CISTAR is to develop the processes that are necessary to take that's widely available and often wasted and transform it into things that can be used in a much more useful way, and to do that in a sustainable way and in a way that has a net carbon footprint lower than what we do today. I didn't put a technical, oops, can you go back for a second? I didn't put in a technical slide as to what actually makes it hard to go from the left to the right. It looks, I'm just moving carbon atoms around. How hard can that be? Well, it turns out it can be pretty challenging, to actually do the types of selective reactions that need to happen. So a big part of CISTAR is chemical transformations. A big part of CISTAR is separations, process optimization, and then it's environmental evaluation to give us feedback on which of our processes are really going to be effective and both economical and environmentally responsible. So those are big challenges. They're not the sorts of things I'm going to solve myself or any one individual is going to solve themselves. So now if you could go to the next. So CISTAR is a National Science Foundation Energy Research Center. So this is the biggest type of activity that the National Science Foundation funds. It's a multi-institutional team. It's led from Purdue, but with a very large contribution from Notre Dame and our other partners at New Mexico, Northwestern, UT Austin. There's probably about 25 to 30 PIs on in total 200 team members if you count all the students that are working in it and other support and other things that the center does. So it's quite a large concerted effort to try to figure out how to go from the left to the right in a responsible way, left to the right on the previous slide. Can you go to the next slide, which I think might be the last? So, part of CISTAR is to do research to enable these transformations, but it's a National Science funded center, and we recognize that to get to a productive future means more than just doing research in the laboratory. There's a large innovation component where we think about how we take what we learn in the laboratory and translate it into practice. So we have industry participants that help us with this. We're involving graduate students, undergraduate students, and so there's a very large educational element of what we do, as well as educational outreach. And we support inclusion goals as well, because we believe that to be really successful, what we want to do, we have to have a diverse team within the center. And I think my next slide is the last slide. And so if you would like to know more, there is some various links and so forth about CISTAR. So I'll end there. Thank you.
Great, and we can open the floor for a quick question from the audience. So I had one, Bill. I was wondering, in terms of process optimization, obviously the initial feedstock is important, right? So the composition of the shale gas,
yes,
which I assume has really large regional, variability.
Yes. Yes.
So do we have data available now as to what the composition of shale gas is in varying regions? How good is the data? Can you comment on that?
Yeah, my understanding is there's excellent data. So that's not my area of expertise. It's an expertise of other people in the team. But yeah, my sense is we have a very good sense of what those compositions look like in different places. And you're absolutely right. There's a large range of variability. Sources that have a lot of methane, sources that have a little bit less, and more of these light hydrocarbon gases like ethane and propane. And that's part of the challenge. In the laboratory, you might work on one molecule, but we needed to develop a process that's going to be robust to to that variation from source to source. And it's a non-trivial thing. But that's an excellent question.
Thank you.
So one of the issues with shale gas, at least as I understand it, is transportation. So are you looking at changing processes to incentivize these oil and gas companies to ship it in their pipeline to a processing center? Or are you looking at converting it on site so that it can be mixed in with the production?
Right, yeah, so the vision is to do as close to the source as possible transformations. That's part of the process optimization and so forth. Does that mean that we put our process at a wellhead? Does it mean that we put it at a regional gas collection facility? That's part of what we're looking at. But yeah, you're absolutely. The other issue is that a shale well might only last a year, and so you can't build a large infrastructure around that because it's not going to be useful for very long. So either you have mobile facilities, or you have regional facilities that you can connect to. And then the goal, of course, is to get to a product that then is either readily usable in the region or is readily transportable to larger centers, what can be used to make whatever one would like to make. That's a good question.
So question, Bill, so the industry in 2020, the crash in demand effectively in a couple of major natural gas companies going through bankruptcies, et cetera, what was the expected partnership with industry, and how has that dynamic changed with the major demand change in, petrochemicals and natural gas this year?
Yeah, that's an excellent question, Paul. So we have an excellent leader of our industrial outreach group, and we're very successful in recruiting industrial partners to the center. I think we're at close to 30, including many of the major players. So an NSF expects that you have those industrial partners. There's an annual membership fee to be part of the center on the order of say, $50,000 a year or something like that. Now, 2020 has been an exceptionally challenging year. And so what NSF allowed us to do was not require the collection of dues this year. Now, what 2021 is going to bring, that's an excellent question. we're hopeful that we'll be able to keep people on board. We have meetings with our industry partners a couple of times a year, and people have stayed engaged. So we don't have indication really that we're going to lose a lot, but it's certainly a concern. You're absolutely right.
All right, so in the interest of time, we're going to move on to the final presentation. So next we have Professor Zhang in the Department of Aerospace and Mechanical Engineering, who will be speaking today about thermoelectric devices for harvesting waste heat. And you can go ahead and unmute yourself.
Okay, yeah. Thank you, Jen. Hello, everyone. Today it's my pleasure to talk about our work in harvesting waste heat. So here I want to first cover just the, okay, sorry. One slide show you the waste heat actually is not big deal, as Paul mentioned in the very beginning. So overall, we are wasting over 60% of the global energy consumption into waste heat. And therefore, if we can harvest even a small portion of that, it can make a huge impact. So here, our lab is trying to harvest the waste heat using this TE device. Here, basically, it's a solid state device can convert heat into power. And I'm showing you, we can basically harvest the waste heat from almost every resource, such as the waste heat in the car, in the power plant, in the factory, in airplane, solar thermal heat. We can also even use our device for cooling. Basically, here we need to use the power, then we can cool these devices. So here's just some principle showing you that we're using this very simple device, physics converting delta T into specific voltage. And we need to basically get the material with very high ZT value in order to convert more heat into power, getting higher efficiency. So here basically we need to design the material in a way to block the heat transport, whereas allow the electrons to flow freely. Because these electron and phonon, they have very small mean-free paths, and therefore our approach is to design the material at the nanoscale in order to control the electron and phonon transport to get the highest performance at the materials level. And here's our approach from bottom up. We can design material to give us the highest ZT, converting more heat into power. So meanwhile, we also need to develop approach to transform this nanoscale material into the macro scale system to make them useful at a low cost. So here our approach is to use a very scalable, low cost printing process. We can then assemble and convert this nanoscale building block into low cost, high performance system to convert the waste heat into useful power. So we have many different printing methods we have developed in the past. One of the printing methods we're using is this aerosol jet printing. We can basically print the device on any substrate, either 2D flat or 3D curved substrate. So after printing, we also have a very fast and efficient technique to sinter the printed particle into a highly dense and high performance flexible device. So here we use this pulsed light to sinter the printed particle on virtually any substrate, like this flexible substrate polyamide papers, which can enable us to develop highly flexible device. Here's one example where we made a very flexible TE device. So here basically we can use them to harvest waste heat even on human body, because there's a huge demand in empowering the wearable devices, sensors. And here one approach we have is to harvest the human body heat, and then we can power this sensor and wearables. Besides developing this small-scale device for powering sensors, we're also working on some much bigger scale device in harvesting the waste heat from the cars, from power plants, and so on. This is one previous DOE project we worked on. The goal is to recover this automotive waste heat from the exhaust, because you all know the car is wasting over 60% of the fuel energy into the waste heat. So our goal is to improve the fuel economy in the car and also reduce the CO2 emission. So this is kind of our device layout. We're designed this a very compact and efficient system to convert the exhaust waste heat in the engine, and we can basically make a very compact, efficient, low-cost system that can be used in harvesting this waste heat. This is our overall process in making this larger scale TEG from the nanoscale particles. So to show you the real impact we can achieve using this nano material or nano technology. And this is a real testing we did using a diesel engine from car, and then we can show you we produced over 1,000 watts of power just by recovering the waste heat in this car engine. And there are still lots of things we can do to harvest waste heat from other places. So overall, we believe that this nanomaterial, nanoscience can play a big impact by using their high performance and also using low-cost process in making them into useful devices. So that's all, and I want to thank our students and sponsors, and also thank you for your attention.
Do we have any questions?
Can I ask? Can you say a little bit about the robustness of the materials, the lifetime? Say an engine's going to last 10 years.
Sure. Yeah, that's a very good question. Actually, we worked with Honda, Bosch, these two big car OEMs. We did lots of tests in thermal cycling, and running the real test for several months or even longer. So this device, because there's no moving part, so they're pretty robust. They can run for years without any maintenance.
So the materials themselves are thermally stable, and interconnects and so forth. They can last a long time.
Yeah, that's actually one key challenge using this nanomaterial. We spend lots of time and energy in making this nanomaterial into thermally and mechanical robust form. So that's kind of the key thing we we worked on in the past. Yeah.
Are the OEMs interested in putting such things into production?
Yes. So Honda, they had huge interest in making this thing happen, and they even selected the Honda Accord as the first pilot car. So but now they're trying to push the cost even lower, because they want to increase the fuel economy with less than $100 per 1% increase of the fuel economy. So but now the cost is really the bottleneck we're trying to address, how to make it really to be cost viable.
Right.
Professor Brenner has a question.
Can you talk a little, obviously always with all the heat that I've got coming off all of these chips, it's always interesting but yeah, specifically, this is the perfect slide. So two related questions. So it seems like sort of a nonlinear decay, right? 1,000 watts at 500. We're down to about a third or a quarter of that in terms of output wattage at like 250 watts when we're coming down to less, we're still at 350 C. So it sort of decays, right? Not surprising, lower energy, low grade heat, not as efficient. So is that true? It's sort of a nonlinear decay when we get to lower and lower grades of heat?
Yeah, actually, it's pretty much showing a very nice linear relationship. And here it's a bit nonlinear because our material itself has a much higher efficiency at higher temperature. If we're using the lower temperature waste heat, we can engineer the material to give us the high efficiency at lower temperature. Therefore, we can, basically it's similar as the kernel, right? With lower temperature, of course, we'll have a lower power, but meanwhile, by making the material perform at that temperature, we can still get a pretty good amount of power, even with lower temperature.
Interesting. And then the follow-on to that, because I see you have, total power, because you got amperage there and you've got watt, and I can figure out voltage. But so what's the volume? If I were to try and change this to like energy in joules, so it's 500 C, but 500 C from a huge volume of energy, right? Versus, so I'm thinking you could get X amount of wattage for what volume of input heat, what joule or et cetera at 500 C, right? So maybe in my mind, I'm sort of missing a parameter there for how much.
You want the efficiency.
Yeah.
Yeah, you want the efficiency.
Sure. Yeah. Efficiency-wise, this demonstration, as far as I can recall, we get about 5 to 6% efficiency in converting the heat into power. So yeah, that's the kind of not very high in terms of efficiency, but considering it's wasted heat, the key metric actually is not efficiency. The key metric is the power density and also cost. If we can get a high power and cost ratio, that's the key.
Yeah. Well, and a lot of these systems, they want to cool anyway. So if you could also think about it as providing cooling as you're pulling this out, the electric out, if that's a secondary benefit, you might be able to like tag on there, right? So I'm going to put heat sinks on all my processors anyway, and they're going to sit at about 100 Celsius, and I've got to pay and architect all those heat sinks, I being the IT enterprise. So if you're also going to say this is a heat sink you'd be paying for anyway, and by the way, I'm going to give you 6 or 10% of your electric back, that might be interesting to a system server developer.
Yes.
I was kind of thinking along those lines in the sense, and an auto engine is like, it's like the hardest application because the temperature is not constant. It's always going up and down, and they work it in a difficult environment. Paul's data center would seem like a much more pleasant place to do such things.
Definitely bill servers. Those are pretty much at peak most of the time.
Sure, yeah. So yeah, we're always looking for new opportunities to apply our technology. Yeah.
So Yanliang,
sure.
You had also used it in the exhaust, right? That's what you were showing, right?
Yeah, the card here actually we're using the card exhaust. Yeah, we also have a project ongoing. We put this TEG in the nuclear reactor core. We want to basically produce the power at the core of the nuclear reactor to power the sensors and enable this, self-power sensor. That's kind of one ongoing effort we're working on. Our TEG survived even in the core of the nuclear reactor.
Yeah. So the question was, I think what Bill was talking about was if you put it in an environment where you are right next to the automobile engine.
Yeah,
that's a different problem than where you have a heat source which is sort of consistent. It's not dynamically variable.
Yes.
Then this application becomes pretty interesting. And also, like Paul is saying, you could have multiple of these small devices and recover heat over larger areas. So those kind of applications becomes a lot more, I would say, attractive when it comes to using the thermoelectrics for heat recovery. So these are like, especially if your 3D printing type approach can produce multiple devices, so arrays of devices.
Yeah.
And use that as a heat recovery system for large surface areas.
Yes. Yeah.
I think we might have had one more question. Jim?
Thanks very much. Thanks for an interesting presentation. I've lived a TAG life for the last 10 years. I got a great application for you, pizza ovens. They're totally worth it. We actually started a company, and we're now actually trying to get into 3 pizza ovens this month to use thermoelectric generators for the application. So I like it. My question is, can you print bismuth telluride really cheap? And in your printing process, do you encounter oxidation of your nanoparticles? Because we found when we SPS them, and now when we're using plasma sintering, the particles oxidize, and it reduces the ZT quite drastically.
Yeah, actually, naturally, yes. The key here in our research is to engineer this particle surface chemistry to prevent the particle from oxidation. So we also work in designing the surfactant to cap the particle to prevent the particle from oxidation, and therefore we can print the material in ambient environment. So to maintain the particle's original performance without any degradation. Meanwhile, it's pretty low cost because here we're using screen printing. It's a very cheap and scalable printing process used to print your T-shirt. Right? So we did lots of cost study, and we find that by printing this material into a very thin film form, we can make the cost to be much lower than a commercial bulk device.
Excellent. And so can you print bismuth telluride that way?
Yes, yeah, sure. Here, our material here is the BIP material. Yeah. Is
it okay? Yes. So my next question is, I would look at the drive cycle of a vehicle, even a diesel vehicle. The operating temperature where you're allowed to place that component is going to be much lower on the lower side, and bismuth telluride is the right sort of material. I think you won't get to the 550. It's just because if you're upstream of the catalytic converter, you're going to take away the heat required for the catalytic converter to reduce the SOx and NOx, right? So you have to be downstream of that from a process point of view. So then you're in a lower operating temperature range. And then if you look at the drive cycle, you're redesigning your thermoelectrics for total joules, not total power. And it's a very different design. I really like the the cost, and I'd like to look at your design a little bit more too. But look at the drive cycle, because it makes a huge difference in the design approach.
Yes, I agree. Yeah, definitely. Yeah, I think we can talk more maybe offline. You can feel free to drop me your email, and we have more conversation.
Yeah, I would love that. That would be fantastic. Thank you.
Sure.
Thank you, everyone. We're coming just about to near the closing of our time together. If there's any last minute questions, feel free to unmute yourself, or you can always send it in a chat. You can manage to type it out super fast. I'd like to take this opportunity to thank ND Energy for hosting this excellent discussion, and for all of the speakers who joined us tonight. Do we have any more questions? Go ahead, Subhash.
Yes, no, I didn't have a question. I had just the final comment. So if there are no further questions, first I would like to thank Professor Schaefer for running an excellent panel. A lot of interesting discussion, and I would say a lot of sort of ideas that came through and potential collaborations. Excuse me, I seem to. So So that concludes our session today. I would like to thank also for all the speakers, presenters, and also the audience that has participated actively. That brings today's sessions to a close, and tomorrow we will start at 1 p.m. sharp. So we'll see you then in large numbers. We had pretty good representation today of all the energy interested people. We hope to get similar involvement tomorrow also. Thank you and have a nice evening, everyone.
Nice evening, everyone.
Good night, all.
Thanks, everyone,
night.
for the great presentations.